Software vulnerabilities are responsible for a significant proportion of security breaches, and most of those vulnerabilities are introduced during the development process. The most cost-effective way to address software security is to build it in from the beginning rather than patch it in after release. Control A.8.25 of ISO 27001, 2022 requires organizations to establish rules for the secure development of software and systems as part of the software development lifecycle. In the next few minutes, we will explore what a secure SDLC requires, how security activities integrate with each development phase, and how the DevSecOps approach embeds security into modern development pipelines. Let us begin by understanding the purpose of Control A.8.25 and why integrating security into the development lifecycle from the start is both more effective and more economical than addressing it after release. Control A.8.25 requires security activities to be integrated into every phase of the software development lifecycle, from requirements through deployment and ongoing maintenance. Security requirements should be defined at the same time as functional requirements, not after the system has been designed and built. Security requirements define what the system must do to protect the confidentiality, integrity, and availability of information, including authentication and authorization requirements, data protection requirements such as encryption and anonymization, audit logging requirements, session management requirements, and requirements for protection against specific attack types relevant to the application. Capturing these requirements early ensures that the system architecture can accommodate them from the start, rather than requiring costly retrofitting of security controls into a design that was not built to support them. Threat modeling during the design phase identifies the security risks inherent in the system architecture before a single line of code is written. By systematically analyzing the system's components, data flows, trust boundaries, and external interfaces, threat modeling uncovers the specific ways an attacker might exploit the design. The STRIDE methodology, identifying spoofing, tampering, repudiation, information disclosure, denial of service, and elevation of privilege threats, provides a structured framework for this analysis. The output of threat modeling is a list of specific threats and the design decisions or controls needed to mitigate them, providing developers with concrete security requirements rather than generic advice. Secure coding standards define the specific practices developers must follow to avoid introducing common vulnerabilities during implementation. Standards typically cover input validation to prevent injection attacks, output encoding to prevent cross-site scripting, authentication and session management implementation, cryptography usage, error handling that does not expose sensitive information, and avoidance of known dangerous API calls. SESD, Static Application Security Testing, analyzes source code for security vulnerabilities without executing the application, catching issues such as SQL injection patterns, hard-coded credentials, and use of deprecated functions. DSD, Dynamic Application Security Testing, tests the running application for vulnerabilities by simulating attacker behavior, identifying issues that only manifest at runtime. The deployment phase of the SDLC should include systematic hardening of the runtime environment, removing unnecessary services and accounts, applying security configuration baselines, and ensuring that the application runs with the minimum privileges required for its function. The maintenance phase requires a patch management process that monitors for newly disclosed vulnerabilities in the application's components, prioritizes patching based on severity and exposure, and deploys patches in a timely manner that balances security urgency against operational risk. Software with unpatched known vulnerabilities in production is one of the most common and exploitable security failures. Equifax's 2017 breach, which exposed 147 million people's personal data, resulted from an unpatched Apache Struts vulnerability. 4 essential concepts that underpin the secure development lifecycle requirements of Control A.8.25. Threat modeling is one of the highest value security activities in the development lifecycle because it identifies architectural security flaws at the point where they are cheapest to fix, before development has begun. The STRIDE methodology provides a systematic approach, but the essential practice is asking adversarial questions about the system being designed. Who are the attackers? What do they want? and how might they abuse the system's legitimate functionality. A threat model produces not just a list of threats, but a design conversation. Many threats identified during modeling can be eliminated through better design choices rather than additional controls, producing a more secure architecture without added complexity. SESD tools integrate into the development workflow as part of the build process or IDE, providing developers with immediate feedback on security issues in their code. The value of SESD is in catching a class of vulnerabilities, particularly injection flaws, use of dangerous functions, and configuration issues, at the point where fixing them is cheapest. SESD integration into CI/CD pipelines enables automatic blocking of code with high-severity security findings, creating a security gate that prevents vulnerable code from progressing to test or production environments. The effectiveness of SASD depends on regular tuning of the rule set to reduce false positives, which consume developer time and lead to alert fatigue. DSD complements SESD by testing the application as it actually behaves when running, finding vulnerabilities that only manifest in the execution context, authentication and session management flaws, server-side request forgery, insecure direct object references, and business logic vulnerabilities that static analysis cannot detect. DSD tools such as OWASP Zap and Burp Suite Professional can be integrated into CI/CD pipelines to run automated scans against test environments as part of the deployment process. The combination of SASD for code-level issues and DSD for runtime behavior provides substantially better coverage than either approach alone. DevSecOps embeds security into the automation and tooling of DevOps delivery pipelines rather than treating it as a separate manual gate. In a DevSecOps pipeline, SESD runs automatically on every code commit. Software composition analysis checks open-source dependencies for known vulnerabilities. DSD runs against every test deployment, and infrastructure as code is scanned for security misconfigurations before deployment. Security findings flow directly into the developer's workflow as bugs rather than arriving weeks later from a separate security team. This shift-left approach, moving security earlier in the development process, reduces the cost of finding and fixing vulnerabilities and makes security a shared responsibility of the development team rather than an external constraint. Now let us explore how we implement a secure development lifecycle in practice, from establishing standards to integrating security tooling into modern development workflows. Implementing a secure SDLC requires written standards, developer training, automated security tooling in CI/CD pipelines, and a governance process that connects security findings to remediation. Secure coding standards are only effective if developers know they exist, understand why they matter, and know how to apply them in the specific languages and frameworks they use. Technology-agnostic standards provide important principles, but insufficient practical guidance. Developers need standards that address the specific vulnerabilities common in Python, Java, JavaScript, or whatever stack they work in, with concrete code examples showing both insecure patterns to avoid and secure implementations to use instead. Security training for developers should be practical, hands-on, and integrated into the development workflow. Gamified training platforms that let developers practice identifying and fixing vulnerabilities in realistic code samples are more effective than one-time awareness sessions. Integrating SASD and software composition analysis into CI/CD pipelines transforms security testing from a periodic manual activity into a continuous, automated part of the build process. Every commit triggers an automatic security scan, and builds that introduce new high-severity findings are blocked from progressing until the issues are resolved. Software composition analysis, which inventories open-source libraries and checks them against vulnerability databases, such as the National Vulnerability Database, is particularly important given that modern applications typically consist largely of third-party components. A single vulnerable dependency can expose the entire application, and SCA provides continuous monitoring of the dependency tree against newly disclosed vulnerabilities, including security requirements in the definition of done. The agreed criteria that must be met before a user story or feature can be considered complete, embeds security into the development team's quality standards rather than treating it as an external audit. A definition of done that includes threat model review for features touching authentication or data handling, SESD findings below a defined severity threshold, and documentation of security-relevant design decisions creates accountability within the team for security outcomes. This approach reflects the DevSecOps philosophy that security is a shared responsibility of the development team, not a separate function that reviews code after it is written. Post-deployment penetration testing provides independent, adversarial validation of the security of significant new applications or major changes. Automated testing tools find common vulnerability patterns, but miss complex logical vulnerabilities, multi-step attack chains, and application-specific issues that require human creativity to discover. A penetration test by experienced security professionals simulates realistic attack scenarios, finding the vulnerabilities that matter most in the specific context of the application. Testing should be conducted after deployment, but before the application is widely publicized, allowing critical findings to be remediated before they are exposed to the broadest possible attacker population. Let us bring together the essential points from our exploration of Control A.8.25. If you want to master all 93 ISO 27001, 2022 Annex A controls and build a certification-ready ISMS, our complete Udemy course provides detailed implementation guidance, templates, and practical examples for every control. Enroll today and take the next step toward ISO 27001 certification. Thank you for watching. If you found this helpful, please like and subscribe for more ISO 27001 control explainers. See you in the next video.